Hi folks, welcome back to Physics with Captain Rod. So the purpose of this video is to go through a projectile problem, and the projectile problem we're going to work on here is basically that this ball is being kicked at an unknown velocity, unknown angle. And our job here is going to be to find the minimum speed and angle that this ball is fired at if it just barely makes it across here at position 2, across this goalpost looking thing, where this distance is 6 meters and then the vertical distance is 3 meters. Right? So I'm getting this problem, this is number 12-86 out of the Hibbler textbook for dynamics. So, all right, in order to work this problem, the first thing we want to do is we got to break the velocity vector down into horizontal and vertical components. This is what we always do in projectile motion. Right, this animal right here, this is v sub o x, initial velocity x direction, and it's equal to v sub o cosine theta. The fact that we don't have values does not matter. I mean, we're still going to work it the same way. If we had a v sub o and a theta, we would have a number here, but we don't, so we're just going to move on. All right, this is the vertical component of the initial velocity vector, y direction, so it's equal to v sub o sine theta. Right. Next step is to what I always call, track the motion of these particles. I usually just draw the velocity graph. So if I were to sketch a graph of velocity, and we're only going to look at x direction as a function of time, the velocity in the x direction isn't changing. It's constant. So this will give me a horizontal graph, and the numerical value would equal v sub o cosine theta. Right. Position against time. Now again, we're talking about in the x direction. Right? If we have constant velocity, position against time would be linear. And it's not too complex to show that the equation for this line is going to be x equals v sub o cosine theta t. All right, now y direction. Our velocity in the y direction is going to be changing. At t equals 0, the y component of the velocity is positive because it's up. Right? And the numerical value is v sub o sine theta. So we're going to start up here somewhere, v sub o sine theta. However, this velocity component is going to change because of gravitational acceleration. The acceleration in the y direction is going to be down in a numerical value of g. So I usually put minus g for the y component of the acceleration. All right, so that means that what we're going to end up with over here is a linear function, and it's going to have negative slope. And we can find that slope by noting that the slope is the acceleration of the object, which is going to be minus g. So the equation for this line, it's not too hard to show, is vy equals v sub o sine theta t minus, v sub o sine theta minus gt. Next, position against time. All right, so y, oops, get rid of that. Y against time is going to be some sort of parabolic equation. I note that as time goes on, y starts at 0, ends up at a maximum value of 3, goes back to 0 with time. So it's going to look something like this. This point on the graph would correspond to this point where the velocity y direction is 0. The equation for this is pretty easy to find because this, our velocity y direction, which is v sub o sine theta minus gt, this is, another way to say it is dy dt. So this can be separated and integrated, and what we're going to end up with is y equals v sub o sine theta t minus 1/2 gt squared. So as far as the physics of this problem is concerned, there's 3 equations to deal with. We got this one, and this one. Right. Now, this problem inherently has 3 unknowns. If we think about position 2, we don't yet know the time. We also don't know the theta, and we don't know the v-min, or the velocity. I'll just say v sub o. These are all 3 unknowns in this problem. Now, because of the wording of the problem, minimum velocity to get us at position 2 here, I might speculate that this might be a 45-degree angle. I'm not going to do that. I'm just going to treat it like it's an unknown here and move on. So we we have three unknowns, and we also have three equations here. 1, 2, 3, with the same unknowns. So we should be able to solve this uniquely. So I'm going to take a moment, pause this, get rid of the graphs, and talk about how to get this algebraically solved. All right, folks, I'm back. Cleaned up my space here. And again, we're working with these three equations here. All right, 1, 2, 3. And again, the unknowns in these equations are the time, the v sub o, and the angle theta. And I'm going to start with this one right here. And I am going to speculate. I'm going to take a, I'm not going to make an assumption here. I've come to the conclusion that if we're talking about the minimum speed to solve this, that means it just barely makes it over. And if that's true, then the y component of the velocity here must be 0. And let me talk a little bit about why. Just for a moment, pretend like it is 0. That means the velocity at this point is this way. Imagine v sub o increasing now ever so slightly. That means two things will happen. One, we'll have a little more clearance here, and two, this will now have a vertical y component, just a small one. And imagine this velocity vector, the v sub o, dropping ever so slightly. This would just barely make it. It would hit the wall. And you have to realize its velocity vector now would have a negative vertical component. So, the right in between those two, this having a vertical component positive and a vertical component negative, would be no vertical component at all. So when this thing goes through this point, we can say that Vy is 0. So first thing I'm going to do here is I'm going to now couple this equation with this one. So from this equation here, we can say that t is equal to v sub o sine theta over g. If we take that expression and we sub it here, our new equation reads x equals v sub o cosine theta t. Keep it in mind that t is v sub o sine theta over g. So that's basically going to do this. It's going to square that, put us a sine theta here, and a g in the bottom. All right. Now, I'm going to take this equation here, this guy, and just store it now. In fact, let me move it off to the side here. So I'm going to take this and just move it up here, put it in the storage, so to speak. All right, now I talk about these two. From this one, right, if we solve that one for for t, we would get t equals x over v sub o cosine theta. So now anywhere I see a t, I can put that expression. So when we take this and we sub it here and here, I'm going to rewrite the resulting equation. What we got is y equals, I'm just going to get to the end here. You can do the algebra yourself. You're going to end up with x tan theta. Right, that's because, again, you're going to get the x from here. And then sine theta over cosine is tangent. And then v sub o in the top, v sub o in the bottom, they're gone. Minus 1/2 g x squared. So I'm just going to put x over v sub o cosine theta squared. So, we've actually accomplished quite a bit. We took it down from 3 equations, 3 unknowns, to 2 equations, 2 unknowns. When I compare this equation and I say, what are the unknowns? So the answer to that is v sub o and theta. Then I take a look at this equation and I ask myself, what are the unknowns? And the answer is v sub o and theta. So they can be combined. And what I'm going to do, I think the easiest thing is to eliminate the v sub o. Solving this one for v sub o squared, it would be v sub o squared equals gx over sine theta cosine theta. And the reason I solve that for v sub o squared is I'm taking a note right here, there is a v sub o squared. So we can sub this here, and we're going to want to do this very cautiously. So we're going to have y equals x tan theta minus 1/2 g. Now I think what I'm going to do is take care of this. I'm going to put x squared over cosine squared theta. Now this stuff is now taken into account. Then we would have 1 over v sub o squared. If I put 1 over this, that would be the same thing as multiplying that thing by sine theta cosine theta over gx. So I'm going to go ahead and do that. So sine theta cosine theta over gx. Right? So again, that's coming from subbing this quantity here and taking a note that this is v sub o squared. So any way you want to work that out, again, what I did is, since we had 1 over v sub o squared, and v sub o squared is equal to this, that would be equivalent to multiplying by sine theta cosine theta over gx. All right, so now y equals x tan theta minus, all right, so looking over to the right, we got kind of lots of good things happening here, I think. All right, so we have the 1/2 is going to have to stay, but these g's cancel. This x will kill off one of these, so we're definitely going to end up with an x in the numerator. This sine stays, but this cosine kills one of these, so we end up with sine over cosine, which is tangent. And now these are like terms. They can be added together. So what we have is y equals 1/2 x tan theta. Now, at this point right here, this equation has only one unknown, theta. So basically we have tan theta is going to equal 2y over x. Taking a look at the problem that we have, y is 3, x is 6, because the coordinates of this point are the 0.63 in meters. So this is going to equal, right, 2 times y is 6 over x, which is 6. Pretty easy to show. This has a solution if theta equals 45 degrees. So I think my part in this problem is done. I'm going to leave it right there because the rest of this is pretty easy. Since we now know that theta is 45 degrees, we can go to any previous work to get the v sub o. Where's the easiest place? Well, taking a look right here. With theta being 45 degrees, cosine 45 degrees, root 2 over 2. Sine 45, root 2 over 2. X is 6 meters. Y is 3 meters. That equation can be solved for v sub o without too much work at all. So, hope this problem helped get 86 kind of figured out. Again, so the algebra at the end was a little tricky, but I think we got her. So, everybody have a great day.